Assailaimalaikum, my examiner and my supervisor Haji Hisham. This is my FYP2 presentation. My research topic is about the advantage of post-tension slab design and the application in BIM workflow. Before the start of my presentation, I want to thank all the people that helped me during my FYP design. Mm, First of all, I want to thank my supervisor, Dr. Haji Badru, his guidance and his assistant to help me in the FYP in this semester and last semester under the MCU situation. And also, I want to thanks to my family. Mm, Last but not least, I want to thanks for the Vigicom BIM company provide the webinar tutorial to teach me how to use the software. And also thanks for the China State Construction Engineering Third Barium provide me the RC structure layout plan as a reference. My presentation is a bit long, so here is a time frame guideline. If you are hurry, you can refer to this where you are interested. Okay, firstly, let's slightly mention about my recall about my methodology. So basically, my plan is to compare between conventional RC structure with post-tension structure. Then find out by the comparison, find out the advantages of post-tension structure, design in the aspect of structure performance, cost of material, also the feasibility of coordination with other subsystems in the building. As we know, post-tension slab eliminates the existence of beam. So in some situation, the post-tension slab need to carry the shear load that was supposed to be carried by the beam elements. And from previous construction failure accident report, there are huge numbers of accidents is caused by the failure of punching shear. So the design of drop panel is significant in PT slab design. With the adding of drop panel so that the structure could have enough shear resistance. Okay, next. So the step one of my study, as I mentioned last slides, I need first I need to decide which code is better to follow to design the PT structure uh, with the drop panel. So then I divide into three um, testing modeling group. So group 0 is a reference group. In group 0, one flat slab will be modeled, and group A is designed based on the Eurocode 2. It consists of two post-tension slabs with a drop panel. One slab is designed and modeled with a standard size of drop panel. The other one is modeled as enlarged size of drop panel. Opposite with group A, group B is designed based on the ACI 318, which is American structure standard. So in group B, it only consists one post-tension slab with a drop panel. The result comparison will be based on 5 aspects: the load balancing percentage, moment capacity ratio, deflection control, punching shear checking, and the usage of construction materials such as the concrete volume, the steel amount, steel weight. Okay, the software that I use to model this PT slab is named called Adapt Building and Adapt PT RC. This software is specially used for post-tension slab design. Mm, After the structure modeling process was completed under the same load combination, I got the results showing as the following, like the punching shear checking, the load balancing percentage, pre-compression checking, moment capacity checking. So all these results I get from the software. Because I have, like I mentioned in my first page, I have one, two, three, four models to be tested and analyzed. So there's a bunch of results snap. So I will put under the appendix. So from this analysis, I get this table. Okay, first table we see is a summarized comparison of load balancing percentage, LBP. This four black dot line is a recommended LBP range of post-tension structure. So the higher LBP is, the less mild steel reinforcement will be used. So which means that EC2 standard use use less mild steel use less additional rebar. However, compared with the EC2 and the flat slab, the ACI 318 fit with the recommended LBP perfectly. So why the perfect LBP is between 50 and 70%, not just go to 80 to 90%? It's because theoretically, indeed, the LBP could be 100% or more than 100%. But due to the difficulties in construction, the pre-stressing tendon is difficult to control the accuracy of internal upwarding force. So it will take higher during construction if the worker is still skilled, and even in the worst case, if the pre-stressing strength lost its strength, so the remaining march still staying functional. So the next table is a comparison of moment capacity ratio. By the definition of moment capacity ratio, it's the maximum demand moment with the moment capacity. So this ratio must be less or equal to. We see this table only ACI 318 satisfied the requirement. So which means that ACI 318 is safest compared with other. Okay, so the third table is deflection control comparison. We see that is different with other table. In the x-axis is L over x, so which means if the x is higher, so the deflection is. We see that the best deflection control is flat slab, then come after 950, then come with L over 800, and then is last one is L over 600. So in this full model, the flat slab have a smallest deflection, then come with ACI 318, then the EC2 inline model have a largest deflection. Okay, so the fourth table is punching shear comparison from the numbers of columns that require punching shear reinforcement. It is obviously that ACI 318 PT structure has the best punching shear resistance ability. So goes to the next. The fifth table is a cost of material. It compares the use age of reinforcement, which is the length of pre-stressing strength, and the additional reinforcement of mild steel bar. We see the flat slab is lowest in the group, and it's lower than group A, and compare with the rest three of them, the ACI use less material compared with the Eurocode, which means use ACI 318 code to design will cost less of a pre-stressing strength and less amount of additional rebar. From these three figures, all three models have its own outstanding aspect. Especially the ACI 318 have an extraordinary ability in the punching shear resistance, and compare with other two group, it basically is better than flat slab in uh, every aspect except the cost of steel. So cost of steel uh, it's reasonable because it added with a drop panel, so it need to cost more material. If you compare the material cost with others, so it's just so as a conclusion, so ACI 318 structure have a comprehensively advantage in structural performance and the material cost. So the next part of my study is to learn the PT slab design procedure in manual. Before use any of the software to design the certain form of structure system, it is necessary to know the hand calculation design and check from A to Z so that when engineer use the software, engineer can judge whether the computer generated design result is correct or not. So the design of PT slab is mainly contained two parts. One is the tendon profile and the tendons number design procedure. The other one is punching shear check procedure. So this is a structure layout plan I got from CSCE third variant. The original drawing is a conventional RC structure. I redesigned use post-tension structure. For practice and study purpose, I only designed the one strip in Y direction, which is Y4. Due to its irregular shape, I have to convert it shape equivalent area rectangular shape for the convenience of my calculation. So this following is predefined before my calculation. We can see that there's allowable stress definition, also the effective force per tendon. So for the effective force in per tendon, this is a calculation for me. We use the effective stressing pre-stressing strength time with the cross-sectional area of one strength, then divide by 100. So the result will be in kilonewton, 118 kilonewton. So I want to mention about my target, which is 15 to 50 to 90% of that. Okay, so first we need to find how many tendons we need to use to carry certain percentage of dead load. So the formula to calculate numbers of tendon required is area time is average pre-compression divided by force per tendon. So for example, in Spain, in the tributary width is 4.6 meter and the 210 millimeter. So we can the cross section. Then now we have a cross sectional area. Average pre-compression is predefined in previous slide. So based on this formula, we find out the final numbers in this span is 14. So due to the tributary, and so the area will also be different. The selected tendons will also be different for different. Okay, next. Okay, next. Uh, then after getting the numbers of tendon in each span, we need to decide the tendon profile or the CGS of tendon in the middle span and in the both end of a span. So from the figure shown in the left top, uh, based on the tendon profile and the jacking force, using these two formula, we can find out the UDL uh, uniform distributed load, the upwarding uniform distributed load generated by the pre-stressing strength. Yeah, here's the result of it. uh, I use I just input the value, location, the heights of the CGS. Then I use Excel to calculate. Okay, so last step we already know the upwarding UDL. So the upwarding UDL, this is upward UDL will cancel a certain amount of downward dead load UDL. So this is how the pre-stressing work in the post-tension slab. And by this step, we can get the load balancing percentage in each span or segment of design. We see that the LBP formula is the upward the upward UDL divided by the total dead load. So as a result, the average LBP is staying 56, which means that the pre-stressing strength balance around the half amount of. Now we already know that the tendons number and the tendons profile. So, but there still need to perform some force and the moment equilibrium check to make sure that the whole design strip is in balance. There are three types of forces generated due to the placement of tendon pre-stressing tendon: the upwarding UDL, the reaction force at and the extra terminating UDL. So from previous step, the upward pre-stressing UDL can be replaced as one single point load in the middle span. So then due to the point load in the middle span, the reaction force will generated in the end of each span. So the middle point load is going up, so the reaction force is going down. So there are different numbers of tendons in different spans. So for the purpose of continuity of slab strip, so one span should connect with the next span stably. So as a detail show in this detailing, so one part of span will extend to the next span in some distance, then terminate it. So this part will also generate some force that need to be taken care of. So from this figure we see that the UDL is going down for the extended part of tendon, and at the end of tendon there is a reaction force going up to cancel this uh, downward UDL force. Okay. So after the check of force equilibrium in the vertical direction, so the moment equilibrium of the whole design strip also need to be checked. Uh, and also the second support is stay in the center of whole span. So I choose to calculate the moment equilibrium about the second support of the design strip Y4. There are four types of moment generated due to the pre-stressing tendon: the upward UDL moment, support reaction moment, uh, terminated dead end, the dead end moment, movement at the face of column due to the shift of tension. So as I learned in the theory of structure, the table shows the summation of moment generated by these loads. The first table is a calculation of UDL moment, and the second table is a summation of support reaction moment. So basically, it's like so. The third moment calculation is terminated the terminated dead end moment. So we know that from previous detail drawing, there's a one dead end. So the extended tendon will generate a downward UDL, and the dead end will generate upward point force. So which generated the following movement about second, and the last movement need to be calculated is due to the shift of centroid of tendon profile. So the above three movement is generated in vertical direction. However, this is a movement that is generated in the horizontal direction might be easy to ignore. We see that the jacking force is acting horizontally, so there is a change of centroid in this direction. So about the second support, so it will generate movement like this and this. So we need to balance this movement also. Okay, so the next slides, after summation, after the summation, after the su okay, next slide. After summation of all the movements, all the four types of movement, the whole span moment should be approximately equal. Then we down with moment checking. Then come with a stress check. As we know, all the pre-stressing concrete design need to be stay under the allowable stress, as well as in the course of pre-stressing concrete design. So the the stress check of PT slab is also necessary. So similar with pre-stressing course, in this formula to get the stress, we need to find these parameters. For example, the moment due to dead load, moment due to live load, and moment due to the PT strength. Also, the section modulus, second moment of area, and also the jacking force. But the jacking force is already given in the previous. Uh, okay, so and these the above three types of moment, and the first two live load and dead load, I'm getting moment value from the adapt PTRC software. You just need to input the data, so it will generate BMD of the dead load and the live load of the whole span respectively. So next moment, due to the pre-stressing tendon, can just simply use this formula to calculate. So as a result, we get a BMD due to three type of. So after getting the moment value, so now we are ready to find the stress. So this is a stress distribution. I made a table, so we can see that most section stress is staying between 0.5 in tension to 3.5 MPa in compression. So I think this result is commonly accepted. The final step of design is to do punching shear check. Punching shear is a type of failure of reinforcement concrete slab subjected to a high localized force. So in flat slab structure, this occurs at the column support. Uh, this failure is due to shear. So this type of failure is critical because there is no visible signs are shown pre. So the step of punching shear check is as follows. First, the control geometry at the face of support. Second, calculate the demand shear at the face of support. Then calculate the maximum allowable shear resistance. The fourth, select and calculate the control section property. The fifth, calculate allowable hypothetical shear stress. And the sixth, the shear reinforcement and the numbers of studs, and the seventh detailing. So we go from the first step one. So step one, you need to find the parameter of control section. So in the Y4 design script, we only have two types of column. So the interior column and edge column. So here is a formula to find the parameter of after we so after we getting the control section parameter from step 1, we can apply the step 1 result into step 2 to find out the demand share at the face of support by using this formula, and also using the shear SFD from the PTRC software. Okay, after step 3, we need to make sure that all the demand shear is lower than the allowable shear resistance, so that we can proceed with step 4. Otherwise, we need to redesign the section. So this is a formula how we the allowable shear resistance. So I want to slightly mention about the concrete compressive strength. It is given in the table 3.1, that one. So the step 4 is to select and calculate the section property of the drop panel. Then we use this formula to find the actual stress in the specific section. Okay, next. So this is the calculation of allowable hypothetical shear stress, which is a VRDC. So, and VRDC also need to make sure that it is bigger than the V minimum plus key I times. Mm, okay, so go to the next step. So next step, we already know the VRDC and VED, so we can find the stress ratio. If the VED divided by VRDC more than larger than 1, so this at this location, this column, it need to be provide a shear reinforcement. If the stress ratio less than 1, the shear check is satisfied, so no need to. So we see that from this value, we see that among the 4 columns, 2 columns shear check is okay. Just provide the minimum rebar that code required. Another 2 columns should provide shear reinforcement based on the calculation. So this formula is the calculation of air reinforcement. So it also need to make sure it's bigger than the minimum. So based on this formula, we can get the table in the side. And so we see that all in column 2 need to provide as so there are the final results of my detailing. The first one is all the first one is all the reinforcement combined in one drawing. The lower one is detailing. So next, the upper one is additional reinforcement layout plan based on the Eurocode 2 we learned in previous semester. So no need to go to detail of this calculation. And the lower drawing is the shear reinforcement layout plan. Different with a conventional RC structure use a shear link as a shear reinforcement. The post-tension slab use a shear stud and rail as a shear reinforcement. What is a shear stud and rail? So it's basically putting the steel bar so and at the bottom with a thin plate, a thin steel band, so which is this part. Uh, so the vertical bar the red dot we call it stats, and the long thing. Uh, Finally, this is a result of comparison of two structural systems in BIM workflow. First, I want to introduce a bit about BIM system. BIM system full name is Building Information Modeling. So, in my design, the BIM system contains features. The architecture model, PT and system, fire distinguish system, electrical lighting system, air conditioning system, and drainage system. So under each system or model, there are still some sub-model, subsystem. So how do we coordinate all these? So the BIM building information model is the ultimate solution. As a current trend of technology revolution, the biggest, well, what BIM did is it uh, which so by converting the 2D drawing, the plan drawing into 3D model. So this is a big step forward for an engineer to visualize design outcome. Next, I want to talk about the workflow that I developed two structure system, conventional RC structure system in BIM workflow, and also post-tension under the BIM workflow. Basically, both workflow is quite similar, but okay. First page is this page is RC workflow. The next, so it's all start with structure design. That I will send the Revit file to Revit file link to the structure engineer. Then structure engineer will the building structure in Revit and import into their own design lines and check. Uh, After the design and analyze, then export back to the Revit. After structure and architecture done with their job, so start. Uh, the other discipline engineer designer can design and model their own subsystem based on the same Revit link. So there are no many chaos like duplicate and missing file. So after all the model is done, because all the model we mentioned we use the same link, so the origin is same and the project location is all the same. So there will be less problem of alignment. So next step, go to coordination and check. In this step, all the model will transfer into Navisworks as a XFO file. And then after a few iteration and adjustment of design of model, project manager will set up a project schedule by uh, and import inside Navisworks to do the construction simulation. So finally come out with a quantity takeoff, which is a BQ, touches the end of design progress. Then we will deliver the model to the in the only difference in here is that uh, in the checking we use of instead of Navisworks. That for the purpose of visualization, the beacons software will be used as a media to do the model combination and clash detection. Same BIM, BIM as a RC structure. Okay, so here's the BIM workflow. The left side is the right side is post tensions. So the top one, the first row is the modeling result. So the local load applies on the line of the floor. The next page is demonstrating the analyzed outcome of RC and PT structure. The first row is a comparison of RC and PT on shear stress distribution. From the table, we see that in the aspect of stress distribution, RC structure stress is concentrating in the secondary beam, PT and the PT structure stress is converging in primary direction of the floor, which is better in load carrying capability. In the aspect of stressing magnitude, the RC structure holding less stress. So the second row is a deflection comparison. From the deflection distribution, RC is mainly occurred of slab, and however the PT deformation is take place at the edge of a cantilever beam. Cantilever, no, there's no beam. There's just slab at the edge of cantilever slab. And if you so the overall from the values magnitude, the RC deflection is higher. Okay, so this page is a clash detection of. The we see that the PT model have less clash point compared with RC model. So after run the clash detection test, the Navisworks will auto-generate a report regarding the clash issue. So this will improve the communication effectiveness among the different departments. So the other software I used in the post-tension slab design workflow is called Visicom to do the clash point checking. Compare with the Navisworks, first it is able to arrange the tendon. This is a tendon. Arrange the tendon layout. It have a better capability in sorting elements based on their features or groups or family. And the displace mode, we can obviously see that it's more comfortable than Navisworks. So the location of clash point is clear. We can customize the color of clashing point. It also have the ability of setting degree of tolerance model combination. So this is very applicable in solving. So next, this is the result of construction simulation. So the figures shown below is a Microsoft project schedule. So we import the Microsoft project schedule inside the timeliner. Then after we import inside timeliner, then we assign the corresponding building element. So during the simulation, we can find the underlying potential by be able to squeeze the schedule shorter by better visualizing the construction progress before the start construction activity. By simulation, I find out that using PT slab, we can see the video construction time could almost reduce half of RC construction time. So finally, let's make a short conclusions throughout this final year project design. I find out that RC structure and PT structure have different features in the location of critical deflection point, the stress distribution along the whole floor. And second, ACI 318M is more suitable for choosing the drop pattern compared with Eurocode 2. And third, using the BIM could pre-detect a lot of mistakes that could happen in construction. By comparison of RC and PT structure, the PT slab have more potential advantage in many aspects, such as like I said before, the performance and also construction time and the cost of material of course. And also design of a PT slab, the target of balancing load percentage and punching shear design is most crucial step to be overchecked. So this is the most too important of design in. Okay, so even I got the previous conclusion, there are still some and issue in my design. So the first issue is a remodeling issue. Uh, in the BIM workflow, after complete the design of structure, the design software such as Prota, couldn't put the rebar plane into model. So at this moment, if we want to use Revit Link to do BQ for the structure part, we need to remodel the reinforcement bar inside the Revit model. Then we can generate the corresponding rebar. Um, and the second improvement is the application of digital construction at site. In future, uh, it, uh, it is believed that the electronic device cost will getting lower and lower. So maybe we can use the tablet or the smartphone to view the model and to measure the distance, to replace the paper drawing and let the worker understand better about which part they are. Also, we can we can we can be feel the building around us and is more is like kind of more advanced VR technology. Okay, that's all for my presentation. Thanks for watching, and thanks again for the examiner and my supervisor Haji Badru Hisham.